Okay, I think we're just right in time. Hello, everyone, and welcome to today's webinar on examining mechanisms and conditional processes, an introduction to mediation and moderation. I am Verna Felipe, ICUDDR's coordinator for educational programs and regional support. While waiting for others to join, let me make some announcements. If you are a faculty member from higher learning institutions, we invite you to sign up for membership. To learn more about our organization, we invite you to visit our website at www.icuddr.org. The link to webinars, conferences, and workshop recordings can be found there, and alternatively, you can also visit our YouTube channel. As a gentle reminder, kindly ensure that your microphones are turned off. For questions during the course of this presentation, type them in the chat box and our speaker will address them at the end of his presentation. Translations for closed captions in various languages are also available. To turn on this feature, click the CC icon at the bottom of your screen. If there's no CC icon at the bottom of your screen, you have to click the More icon or the three horizontal dots to locate it. Afterwards, you can turn on translation and select the closed caption languages of your choice. And lastly, as a reminder, this webinar is being recorded. So our speaker for today is an assistant professor at the Department of Human and Family Development Studies, College of Human Ecology at the University of the Philippines, Los Banos. He graduated with a Bachelor of Science in Psychology with Latin honors at Ateneo de Naga University. Afterwards, he took up a Master of Arts in Education, major in guidance at the University of the Philippines, Diliman, and just recently completed his Doctor of Philosophy in Addictive Disorders and Recovery Studies at Texas Tech University. He is a Philippine registered psychometrician and licensed professional teacher. His program of research, extension, and community engagement focus on individual and family resilience, adolescent and adult development, gender and sexuality, mental health and psychosocial support, and substance use in marginalized and minoritized communities, especially among sexually and gender diverse subpopulations. His commitment to service is seen in his various civic society engagement, including being the program coordinator of PINTIC Adolescent Development Psychosocial Support Program. He also has numerous publications under his accomplishments. So, ladies and gentlemen, I'll turn you over to our speaker for today, Dr. Nephtaly Joel B. Botor.
Thank you very much, Ms. Verna, for that kind introduction. And good day to everyone who are participating in this activity. I'm joining in from the Philippines. It's 8 in the evening here, where I am right now. And I suppose we are joined by people coming from different parts of the world. So you have a great day, everyone. And thank you for joining us in this webinar on mediation and moderation. So when I was thinking about the title for this sessions that I'm going to facilitate today and in the following week, I was actually thinking of a the most appropriate clincher which can summarize what we're going to have in the two sessions that we will be having. And as I was planning for it, I realized that the best clincher really is examining mechanisms and conditional processes. So mediation and moderation, as we will learn as we go along in this webinar, are statistical approaches. These are data analytic approaches. But as behavioral scientists, as practitioners, these statistics are actually helping us understand more about mechanisms and conditional processes. So this is the real life application of these two techniques. And as I go about with my sharing today, I hope that we keep that in mind, that although there is mathematics in what we're going to talk about. There's statistics in what we're going to talk about. All these boil down to our interest, our desire to understand real life situations and real life mechanisms that we observe in our communities, in the clients that we work with, and in our day-to-day lives. So in the 2-day session, we're going to start today by revisiting simple and multiple linear regression and its assumptions. Then we will start talking about mediation analysis and the salient issues that we need to focus on or consider when we are using this technique. And on the second day, which is the following week, we'll have a very quick revisiting of mediation, whatever we will accomplish today. Then we will go directly to moderation analysis, conditional process models, and salient issues in moderation. Now, there might be a possibility because of the bulk of content that some of the topics that we want to discuss today will we will not be able to finish it. So it depends on our progress. If that happens, all those topics will be carried on in the next week. So there are just a couple of questions that a few questions that we want to answer, and there's a quiz or a poll that you are seeing right now. So we want to have just to have a sense on which of these quantitative approaches you have experienced working on. So there are a few questions. If, say, for instance, have you experienced estimating descriptive statistics? Have you experienced estimating group differences? If you have done some work using correlations or even simple and or multiple regressions. So it will help us to know where we are. So we will appreciate if you can answer this poll. Following that, there's also a question in number 5, wherein we just wanted to know which of the following softwares you have used for data analysis in the past. So these are um, a list of softwares that people tend to use when they run quantitative data analysis. All right, so I suppose most of you have already answered the poll, and it's just a way for us to sense what. So most of us have experience estimating descriptives and group differences, correlations. So there's a good mix of participants in terms of our training and experience. Then most of us are Excel and SPSS users. All right. There's some of us who used M+, R, and Jamovi, and like a small number who used Python. So just to level off, I'll be using M plus mostly for discussion purposes, but there are a lot of softwares available for the things that we're going to do, and they can be readily implemented using the software of your choice. So I had certain assumptions when I was preparing this presentation. First is that I assume that there's diversity in quantitative training, as the poll also validated. We're a good mix of people with experience in doing all sorts of analyses. But the main assumption that I have is that at least we have basic knowledge on hypothesis testing, correlation, and some simple linear regression. I also assume that you would be using different softwares, and we would have different analytic orientation, especially those who have already been doing quantitative data analyses. And these experiences that we have in the past will help us get to know the materials better. But if we haven't done it, we will also be having some review of those basic information. So we will use algebraic formula whenever necessary to clarify concepts. This is something that I have learned in my experience and training, that it's always good to have some familiarity with these formulas, but we will not go into the details of them. And as much as possible, we will use them sparingly. There's a good metaphor that I learned through my mentors in the past, and like since most of us are practitioners or scholars in a very specific content area, which is addiction and recovery. But the metaphor is this: like when we do statistical analyses, we are the drivers of a car, right? So we are drivers riding a car. Car is statistics. We should be able to navigate it, and we should have some basic orientation at least on how the machine inside the car works, and that's where the algebra would help. But there's also uh the reality that that in itself is a very specific field. So um, it's good to have some mechanic or an engineer to help us fix those things, and these are things that statisticians do, right? So that's a nice and empowering metaphor that I always keep in mind every time I do statistical analysis, or I teach my students about statistical analysis. So our focus is on explaining the underlying reasons why we do the specific techniques, and demonstrate the how of estimating models and interpreting results based on essential parameters. All of us are consumers of knowledge products like journal articles, or all of us attend conferences and we hear like a speaker, um, say something about these very fancy methods that they use. So it's good to know at least how they are able to arrive at those conclusions based on the different statistics that they do. But at the same time, all of us practitioners are also encouraged to do research, because with the scientist practitioner teacher model, which is already becoming more and more necessary in the world today, it's good to have these things in our toolkit as practitioners, researchers, or scientists, practitioners, and teachers. Right. So with those being said, I want to start our discussion with uh some form of like a scenario. We're having this scenario. So let us first imagine ourselves passing by a bar and seeing a group of people drinking alcoholic beverages. Since we are behavioral and social scientists, we're inherently curious. So we always think that there's more than meets the eye. So lots of thoughts started running in our head. And there is this little but recurrent voice asking the very important question that wouldn't let you sleep. So the question is, why are these people drinking? So said differently, what could be motivating their decision to drink, and what are the factors that lead them to consume alcohol? From this observation and the pressing question that wakes you up at 3 a.m., you started thinking backwards, probably going back to a paper, a journal article you read, or a TED talk you watch, or just going back to your own experience, what you have observed from your peers, or even what you heard from people that you are working with in your practice, and ended up with an educated guess that maybe these people you saw drinking have recently experienced a distressing event in their lives which led them to drink. So this is probably the thought that came in your mind. Probably they are drinking because they are stressed. So think, for instance, a college student who failed an exam, or an adult who just came out of a heartbreak, or an older person who is faced with the challenges of retirement. So all these individuals have experienced a significantly distressing event or a change in their usual activities, which probably takes a toll on their psychosocial equilibrium and led them to drink to cope. So this is your thought process. Of course, there could be other reasons, but this is what the reason that first came into your mind. So, given this thought process, you wanted to capture that real life event and what you made sense of it through a representation. You ended up with this picture here. So, you took your pencil and wrote. So, you ended up with this. There's a box on the left indicating distressing event, a box on the right indicating alcohol consumption, and a single headed arrow connecting the two boxes, wherein the arrowhead is pointing towards the right. So simply, this is a schematic or a diagram which shows your belief about that real world event, wherein you have a belief, a guess, an educated guess, because you've read and you've done your practice, that a distressing event is what probably motivates or what leads to alcohol consumption. This simplified representation of reality is referred to as a model. And in this two-way webinar, we will be talking a lot about models and model building. Because as you will see later on, as we get more complex, the process, the journey is nothing more than just building a model, a more complex model than what we had thought about before. So it's basically incorporating more and more beliefs into that model that you have. In short, just a model is just a fancy way of simplifying realities into a format which we can easily examine and make sense of. Now, putting on your researcher's hat, we refer to this as our conceptual model, which shows what are variables, stress, which we will now denote as X, and alcohol consumption, which we will now denote as Y, and how our variables, stress, distressing event, and alcohol consumption relate to one another. That's the arrow moving from left to right. Since we wanted to have more evidence that could support this model, we gathered data or instances or reports of a real world event happening that could answer the underlying question to this model, which is now formally articulated as, does experiencing a distressing event lead to alcohol consumption? So for us who have been doing research, this is our research question, which basically is just a re-articulation of our belief, our model. Questions about how you will design your study to gather the data you need is a whole gamut of discussion. So, will I do survey? Who are the people that will be involved in this survey so that I can gather data from the real world? Is a whole different discussion. It's an important discussion, but it's a whole discussion on its own that and hence we will not delve into discussing this in the webinars. We will just imagine, for instance, that you decided to conduct a survey among a few hundreds of individuals, and you now have all sorts of data that you can analyze. So probably you ask them, You get, say, 600 individuals to answer a survey asking them if they have experienced distressing event, or how many distressing events they have experienced in the past week or past 6 months. And then you also ask them about whether they consumed alcohol, or maybe you decided to use a more commonly used scale like audit to measure alcohol consumption. The whole process, which we imagined just now, shows how we conceptualize and build a research question which could be addressed through the use of regression analyses and its extensions. I thought that I needed to start with that one, with that emphasis on model and model building, so that we have an appreciation about why we are doing this in the first place. The simple model that we have, distressing event, an arrow, and alcohol consumption, is actually a simple linear regression model, which could also be re-articulated using this algebraic formula. For us who likes math, uh, this is the equation of a line. Uh, and we have probably encountered this in our high school algebra or college algebra. This is going to be our friend in the next days. So the equation of a line says that y is equal to BO plus B1x plus E. So what do these terms mean? The y now becomes our dependent variable or outcome. So it's blue. So it's alcohol consumption. The BO is the intercept. So it's in simpler terms, it's the value of our dependent variable when x is 0. And x here is our independent variable or predictor or the explanatory variable. This is the stressing event in this picture here. What we're interested in uh, really is the slope, this one in purple. So the slope, in simpler terms, just show us, look, if this is x and this is y, what is the relationship between the two, and how big or small the relationship is, and what is the direction of that relationship. We can re-articulate this model further by presenting them in this form, in this figure. So the distressing event, which is our x, our explanatory variable, goes on to the x-axis, the one in red. Our y, which is our outcome, goes to the left. That's alcohol consumption. And all the points that we have from the data that we gathered could be plotted in this format. So each of these black dots are cases. These are data. These are individuals from whom you have observed through the survey, and you are plotting their scores in this line. Now, say for example, you have already used this equation, and the line, the purple line is leaning towards the right as on figure 1, then you have uh, a, a direct or a positive slope, meaning as the distressing event increases, then alcohol consumption is also increasing. So that's a direct relationship there. If you get, say for example, after plotting those points, you get a picture like on the right, this is an inverse or a negative slope, which means that as the stressing event increases, alcohol consumption also is decreasing. So it's an inverse association. Many of us have done correlations, and that would mean that many is familiar with this kind of representation of the model. And we usually call this a scatter plot. So this scatter plot will still be useful when we do regression and even in more complex extensions of the technique. Okay. Now, so what is that statistics doing? How is this formula? How is this formula that we have uh acting out behind the scene? So what is it actually doing behind the scenes? So we have this Venn diagram here, wherein alcohol consumption and distressing events are represented as overlapping circles. So these are associations, basically associations. And the the purple, the slope is no more than just the intersection between these two variables. So that's we also call this the effect, or the direct effect, or the mean effect of uh distressing event on alcohol consumption. Right. Now, given this model, so we already have these models in mind, these illustrations, we are now ready to estimate the data. And as I mentioned earlier, the data that represents the real life event, how you get to it is a totally different, is a totally complex conversation. But for the purpose of this demonstration, I simulated some data that I used to create uh, this model to estimate the model. So once you have a model in mind, once you have the data in mind, then you proceed to model estimation. Okay. So this is a simulated data of 600 individuals. As you consider, for simplicity, all variables are in z-score metric. So z-score is just it's just a score which wherein the mean is 0 and the standard deviation is 1. So you can rescale your raw scores into z-scores. In actual data, we don't usually use z-scores. So this is just a caveat to this. We don't usually use z-scores before we project them into a regression. But this is just a rescaling for simplicity's sake. As as I began my presentation earlier, I mentioned that I'm mostly an M plus user, and that's because it's also partly training, because that's where I have been intensively trained. I also use R on the side. But I like M plus because it is straightforward. I'm not selling M plus, or I'm not part of the organization which developers sells it. But if you want really a solid and robust statistical analysis with, if and you have like very minimal coding training, then M plus is a way to go. The only thing is M plus is for a fee. So R on the other hand is free, but it takes some additional training for coding it. Although with the open science trajectory in the field, you can basically find M plus codes available online in GitHub, for example, and just make use of these syntaxes in to fit like to implement your analysis. But M plus for me is nice because it's robust and it's very easy to use as well. There's another software that I use mostly for instructional purposes, and that is Jamovi. This is also an open source software. Um, One thing that I like about Jamovi is that it's, aside from it's an open source, is because it has a graphical user interface, much more like SPSS. So if you download Jamovi and make use of that, you will have the same feel as you do if you're having SPSS. So it's a nice transition from SPSS to Jamovi. And there are also a lot of statistical packages that are developed by user developed statistical packages which you can access to in Jamovi. And for what we're doing now, we are using this regression uh, package. Most of the packages here are also developed using R. So if you want R, but you want a graphical user interface, then Jamovi is the way to go. So as you can see here, I'll use the M plus as my discussion for exhibit, because it's very apparent here what we're doing. So there's a title there, simple linear regression model. There's data. So data is from CSV file. The variables that I have here are represented in the names. So this is sloth, is self-loathing, hatred, negative affect, alcohol use, distressing event, age, and gender. So all these variables are in the data set that I have. But for this analysis, for this estimation, I'm only going to use alcohol use and distressing events. So only these two. Okay. So analysis here is as you can see, is estimator equals ML. So that's maximum likelihood. We'll talk about it a little more probably at the end of everything, because this is an analytic decision that you have to make, like what estimator you're going to use, and each estimator would have their own strengths and quirks. So for these analyses, I'm just using maximum likelihood, because it's just good if you're using maximum likelihood. This is it's good in accounting for missing data. It's good for accounting for non-normality and all other assumptions. The model that we have, as you can see here, this model, and I'll be flashing it back again, distressing event on on alcohol consumption is shown here. So ALCUs on distress. Now this is a little confusing perhaps for a starter. Why is the arrow from distress to ALCUs? Uh, the M plus was developed to follow the the uh, the way the formula is usually read, and that is X on Y. So I'm sorry, Y on X. So alcohol use on your independent variable. So the alcus here is your Y, is your outcome on X. And I included distress and alcus here. Just we mentioned it. And in a short in a short explanation, this is just to help in handling missing values. Because when you call in this one, distress and alcus, your variables using this format in M plus, you're actually doing what is called the full information maximum likelihood, which only means that you are making use of all the data in these two variables to make the estimation. So that's why I mentioned that ML is good if you are having some missing data issues. Then output stdyx here on the lower left of the screen only tells the software that you have to call in for standardized values. Then tech one, this is an M plus specific process or function, which only gives you a hint if there are some estimation problems. Then plot, type 1 is plot, so it gives you the basic descriptive plots, and that would include the scatter plot that I showed you earlier. So this kind of plot could be generated also using M+. Now in R, as you can see here, this is basically there are a lot of ways actually to estimate a regression in R, but I'm using the base R function, which means that I'm not using a user created package when I'm estimating the regression model here. I'm just using whatever is default used in R. So that's the LM function here. So this is SLR is you're creating this simple linear regression object here. Then you use the LM function. It tells R, hey, you estimate a linear model, a regression model, wherein alcohol use is your dependent variable, your outcome. The tilde on the upper right box here is uh, the the symbol for that regression analysis, and distress is your explanatory variable. Then you have a comma here. Data equals df. So this is df. I've created df as my data frame, which is similar to the data set that CSV here. So it's just a single line in R, but there are lots of lines before that. Before you reach that, you have to clean and prepare your data and label your data as appropriate, and then you call in this regression model. Then the way you can get the regression statistics, if you do summary, then function SLR. So that's just an example of how you do it in R. In Jamovie, you use this regression function, as I mentioned earlier. Then the graphical user interface will show you all of the variables in your data set. You just have to point and click the arrow. So the dependent variable is alc use, alcohol consumption. Then you don't have an X there or a predictor, but you have their covariates. Okay. So the covariates there, this is where you place in your uh, independent variable or your explanatory variable. Right. So let's take a look at the plots. So this is Jamovi plot, the scatter plot that I showed you earlier. This is how it looks like using the data that we have simulated. Um, on the right is the R plot. So that's the lots of line here. I have to use ggplot to be able to generate this kind of plot. Uh, then in M plus, this is how the plot looks like. Right? The advantage of R, in my experience, is I do like beautiful plots, beautiful and colorful plots, because it usually helps convey the message. I mean, it conveys the message well, as opposed to numerical stuff, which we will be seeing in a while. But because of the plot already gives you an idea, oh, there is a direct association between distress and alcohol consumption. So that gives us an idea already. So if you are like me, who likes beautiful plots and colorful plots, then you may want to use R for that purpose, right? Or in what I do, if I'm using M plus, so I generate, because in M plus you can also um like download the values for this. So I download, I save the data which was used for this plot. I put it in Excel and create, all those beautiful graphs using Excel. So you have lots of options when you want to draw these plots. Jamovie plot, I think, is already good as is. So I would, if you're using Jamovie, it will automatically show also on the results pane. Let's now go to the model parameters. So this is what you're getting from uh, the results. So after running them, this is now what you'll get. Um, in M plus, what you're seeing on the top, 2.204, is the unstandardized slope. It's the unstandardized effect or value of the association between distress and alcohol use. So for every 1 unit increase in distress, there's a 2.204 unit increase in the alcohol use. So that's what we're seeing here. So that's the estimate. Then below that, just on the left pane of this presentation, a little below, you will see STDYX standardization. So this is now the standard values, the standard slope estimates, the beta or the beta of the equation. You're seeing here 0.632. So this is a standardized value, and this shows the association and standard deviation metrics. So the unstandardized value on top, 2.204, shows the value and the metrics of the actual the scores, the metrics of the actual scores that you have gathered. The standardized value below is in standard deviation metrics. So if you remember the normal curve and the standard deviation is the distance from the mean. So it's a measure of variation. It's a measure of dispersion. So how do you make sense of this? Simply, if you see, given this value, 0.632, it only tells us that for every one standard deviation increase in the x, in the stress, there is a 0.632 standard deviation unit increase in the y. So that's basically what this is saying. And another important thing to look for in this kinds of analyses is the R squared. So the R squared is simply the variance in the outcome, which is explained by the predictor. So this is the variance or the variability in alcohol outcomes or alcohol consumption, which is explained by distress or distressing event. Now, is there a rule of thumb here? We have to remember that this is a measure of effect. So this is in a way, the effect of distressing event on alcohol use. The highest possible effect would be 1, which is in my mind, it would mean as if the distressing and alcohol use are basically the same thing, but they are not the same thing. There are other things explaining alcohol use other than distress. So the point for here is is a good number. It means that if you translate it into percentage, so we can say we translate it into percentage metrics. It's basically just 40% of alcohol consumption is explained by distress. This is already a high number for the things that we in the social and behavioral science are usually working on. And if you look at R and Jamovi, you can see that these are comparable. In Jamovi, you see exactly the same values. In R, you see a little bit of difference, and usually it's because of estimation, what's happening at the back end. There it may be because of rounding off differences in the way these statistical softwares round off as the estimated value. So having seen all of those, we go back again to the model that we have. So distressing event to alcohol consumption. We go back to that schematic on top, and we reminded ourselves with this equation of a line and our initial, which represents our belief system. And then we go back to the question that we have. So does experiencing a distressing event lead to alcohol consumption? Then, because we have done all this process of estimation, then we have examined our data and estimated our parameters. So parameters are basically just things that we estimate, like slopes. Then we have an answer to our question. The way we can write that on a report using APA format is the one inside the red box. So we could say that a simple regression analysis that we have done showed that individuals who reported greater experience of a distressing event also reported more alcohol consumption. Then we cite or we indicate there the parameter estimates and the p-values that we have. The p-values that we see here, p less than 0.05, is derived from these values circled with a blue circle. So these are the p-values. Now, there are certain assumptions in linear regression, and we just a mnemonics that helps me and my students learn it or be familiar with it is the mnemonics line. L stands for linearity, I for independence, N for normality. But the kind of normality that we're interested here is multivariate, and we'll explain it a little bit as we go along. Then E stands for equality or equally distributed residual variance. In our statistics class, we usually refer to this as homoscedasticity. And another one is no outliers or influential cases. So let's talk about these one by one in a nutshell. So by linearity, we mean that there is a linear relationship between the x and the y. Because there can be all sorts of relationship between x and the y. It may not be linear. It may be curvilinear. Curvilinear. It can be like a parabola or a curve. So when that happens, we might need to uh, either account for that in our model estimation, or we may think about using a different approach. So how do you examine linearity? There are specific techniques. So we can use a QQ plot to estimate it. So this is just basically plotting in the standardized residuals along a quartiles. So if you do QQ plot as your approach, then you want to have all the lines lining up in a nice line like the one on the left. Or another approach would be to use a residual plot, wherein you plot the residuals along the fitted scores or the estimated values. Now I'm using the word residual here, and I will go back a bit to one of the slides that we used or that I showed you earlier. So there's a line here that shows the x and the y, the plotting the association or the relationship between the x and the y. And the purple line here is uh the best fit line. So this is the line that shows what is really the trajectory or the pattern in this relationship. Now we cannot expect that all of the individuals would have exactly would have scores that would exactly fit the line. So there would be some difference between the actual score of the individuals and the trend line or the best fit line here. Now the difference between the score of the individual and the estimated trend line is what you call the residual. Um, in simple terms, a residual is just a measure of error, an error in estimation. So uh what are the things that are not accounted for by these models? And this is also the E here um in the equation. So that's the residual. So the residuals when they are plotted with the fitted or the estimated values, there should be some randomness here. So unlike in the QQ plot wherein you want some nicely linear trend in the graph, you want something random here. You don't want them to assume a specific shape, which is an indicative that maybe there is non-linearity in your model. Right? So the I independence only indicates that observations are independent and that residuals are independent. So the errors are not influencing each other, and that the observations are not independent from one that are independent from one another. So it's also associated with the linearity assumption. There are ways through which you can examine it, and now you use a test statistic. The most commonly used is Durbin-Watson test, which indicates autocorrelation among the residuals, meaning that there are some relationship between the residuals. So the rule of thumb is shown there that if the d value is 2, then we can assume no autocorrelation. If the d is smaller than 2, then there is positive autocorrelation. And if d is greater than 2, then there's negative autocorrelation. What we want all now the value would usually have a p value associated with it. Therefore, the null hypothesis for a Durbin-Watson test is that there is no autocorrelation. This is what we want. We don't want to reject the null hypothesis in these models. Another way of dealing with independence or ensuring independence is in terms of the design. Now, the test statistics, you can do this once you have the data, but to getting the data, prior to in doing your survey, making sure that there are no two or more data points from the same case is important. So this now falls this is a responsibility that we need to satisfy prior to analyzing our regression model. We haven't talked about data cleaning and data preparation, but this is where you ensure that every case, that every data point in your variable are representing unique cases. Right. So the N normality assumption only say that the errors are multivariate normal, or the joint distribution of the variables follows a multivariate normal distribution. The joint distribution here uh, would could mean could mean only that the relationship between there is there is normality considering both the value of the x and the y. There's a technical explanation to it, but to just to have like a simple hands like a handle in our mind, the multivariate normal here is already factoring in the normality of both the x and the y, or all the variables in your model. Now, this is different from the usual normality statistics that we normality plots that we use using only one variable. So that's univariate statistics. Uh, the way we examine normality is, again, we can use the QQ plot to do it. So the same way that we assessed linearity. But there are also other test statistics that you can use. So Mardi's test examines both the skewness and the kurtosis. So this is multivariate skewness and multivariate kurtosis. So the skewness is whether there is a tail in the distribution, and the kurtosis is whether the distribution or the bell curve is peaked or it's flat, right? So we want a normal uh curve in essentially we want the curve to have relatively symmetrical shape, and relatively uh mesocurtic shape. So just right, just not too peaked or not too flat. So the hypothesis there is that the test statistic follows a normal distribution. So when we use this test, this is your null hypothesis that the test statistic follows a normal distribution. The alternative is that the test statistic does not follow a normal distribution. We don't want to reject the null hypothesis here. So we are if the if we reject the null hypothesis, then it means that, or if the p-value of the Mergia test is uh below point is greater than 0.05, then the test statistics that does not follow a normal distribution. Equality of residual variance or homoscedasticity only indicates that the variance of the residuals are constantly distributed across all levels of the predictor or of X. So we don't want, when we do our plots, we don't want a unique, like a weird shape here. So we want it to be random. The errors should not have any specific pattern here. So we can examine homoscedasticity through graphical approaches, again using QQ plot or residual plot, which I showed you earlier, or you can make use of the spread level plot. This is not available in M+, but you can easily do this in R. So this is an example of a spread level plot. So if you're using a test statistics, then you're using a Brush-Pagan test, which examines heteroscedasticity. Now, this test is not a test of homoscedasticity. Technically, it's a test of heteroscedasticity, meaning it tests whether the variants are not equally or are not constantly or equally distributed. So the null hypothesis here is that the variance of the residuals is constant, and the alternative hypothesis is that the variance of the residuals is not constant. So probably as you're seeing now in terms of the assumptions, these are assumptions that we can only test after we have done an initial estimation of the data. So unlike probably common belief that the assumptions could be tested before you estimate, as you are seeing now, these assumptions can actually be estimated only once you have already gathered the data and made some initial regression estimation of the data. Then finally, no outliers. So there are no outliers, extreme values, or influential cases that severely skews the analysis. In regression or in any other statistical tests, outliers, we are usually careful about outliers. Now, whether to remove or retain them is an executive decision. It has to be done really thoughtfully because say for example, I can't take off all the outliers here and I'm only left with this data. But before removing them, you should already have some reflection or contemplation. Are these outlier really outlier? Are these really meaningless data, or are they uh showing a different aspect of the phenomenon that I'm studying? So there has to be some reflection also when looking at outliers. And these are just some of the way to examine outliers. So you have leverage plots, you have Cook's plot and influence plot. So these are easily generated also using R when you make use of R. So the thing here is that outliers and extreme values usually skews our result, because remember what we're trying to do is we are predicting an outcome based on the value of the predictor. And what if there are extremely high values in the predictor? So that can also have an impact on the model estimation. But again, this is something that has to be done really mindfully and thoughtfully before taking away all the outliers and removing all the extreme values. Now, we have seen and reviewed simple linear regression, and I started exhaustively talking about that because the succeeding discussion are founded on those assumptions and those ways of looking at things. So that's a simple model that we have, but everything begins in that model. So there's a nice quote here that I took while I was reflecting as I was preparing this presentation. It says, "The world is a thing of utter inordinate complexity and richness and strangeness that is absolutely awesome." So it's just so beautiful and complex and rich. The implication of that is when we do our modeling, we also want to have uh, those complexities built in our model or in the estimation that we do. So if you see here, what you're seeing is a model which still has the stressing event as an explanatory variable and alcohol consumption as our outcome, but we have factored in a couple of other variables which could have an influence in this relationship. For this example, I include age and I included assigned sex. How did I end up including these two? One, I could have, and the way we do it in is really you read the literature, look at the literature. Is age really influential in terms of alcohol consumption? Are there studies showing that older people tend to consume less than younger people? Then assigned sex, are there studies showing that male individuals or individuals who are assigned as male at birth tend to consume more alcohol consumption than those individuals who are assigned female? So if these inclusion of age and assigned sex is not haphazard, this is also founded upon prior knowledge. So these addition of the two variables now calls for uh, what we call a multiple linear regression. And what we're doing here, since we have expanded our model, our representation of the world, and that is shown schematically on the image above, we also expand our equation. So we are also factoring in now uh, these additional variables there. B, B2, which the X2, which is age, and X3. So those in red, if you remember earlier, are predictor variables. Then the ones in purple are still slopes. Right? The one in purple are still slopes. The one in X are still predictors. These are the data that we have. The beta 0 here is still the intercept, which is the value of y or the value of the outcome when all of the predictors are 0. And y here is still our dependent variable. And this is the reason why I emphasized earlier that having some basic familiarity with the equation of a line is going to help us in the process. Because what we really are doing as we go through the journey of answering that research question we have, does this stressing event lead to alcohol consumption? What we're actually doing is just we are building from that simple regression model, adding in variables that we think are important to consider before we make that conclusion later on. So just like what I showed you earlier in terms of the Venn diagram, the overlapping circles, this is now how the model looks like. It's a bit uh complex now, even as we added only two variables, age and assigned sex. And what we are interested in is the effect on Y. Still, that's still our interest. We're still interested about the outcome, but we're factoring in uh, the influence of age and assigned sex in that association. Right. So what happens in the model estimation? So we still have these similar syntax that we had when we did the simple regression, but we added only age and gender. In the M plus syntax, you see that in red. So alcohol use, consumption, on distress, then age, gender. Then I also call in age and gender here to account for missing data. So it's not as daunting. If you start with the simple regression as we build the model, it's not as daunting and as scary anymore. Because we only, what what we are seeing now is that basically we are just adding two variables in the model. And we added those variables again because we have an argument to be made based on prior research that age and gender should be factored in the model. Say, for example, we did the estimation already. Now we have the model parameters for this multiple regression model that we have. Right. So on the screen right now, you're seeing the unstandardized parameters or the unstandardized results, which again shows the results in the original metrics of the data. So we see here that for every 1 unit increase in the X, there's a 2.199 unit increase in Y. Not much of a difference from what we had earlier. And it's also significant because the p-value is less than 0.05. What is added here are age and gender because we added them in the syntax. So what we're seeing here, 1.798, and its p-value is 0.000, which means it's significant. When we added gender, it's negative 0.311. The p-value is 0.068, so it's not significant. Meaning gender doesn't really, in this fabricated data, gender doesn't really matter statistically. It's the age that matters. And we also have the standardized parameters here, 0.631, and p-value is less than 0.05. So that's, if that's what we're using as a basis. This again is in standard deviation units. So for every one standard deviation unit increase in X, there's a 0.631 standard deviation unit increase in Y. Again, we're seeing age here and gender as our additional variable. Now, you have a choice in terms of interpreting these results. And this now becomes part of your theorizing and your conceptualizing. So are you interested in age and gender equally as a predictor, or are you only accounting for the presence of age and gender in your model? What do I mean? Is your question, does age, gender, and alcohol use lead to alcohol consumption? Meaning all of these are your explanatory variables. So this is a multiple regression question. Or in most cases, and as you probably would see in some of the articles that you have read in the past, sometimes social demographic informations are treated as covariates, meaning you're just accounting for their presence, but your main model is still the association between the X and the Y. So in this example, I could say that the association between distress and alcohol use is positive and significant, accounting for age and gender. So you're only accounting for the age and gender of the participants. So either way, this is it's a multiple regression question. There are other extensions of multiple regression wherein you do it hierarchically. Uh, for instance, you enter first the social demographic variable, then you estimate all the variables, then you compare if there is any a change in R squared. So that's another extension of a multiple regression uh estimation. So these are your options if you have these questions in mind. And this is the decision now is based upon your theorizing and your what really you want to examine in these using these strategies or techniques. Now there's an initial additional assumption in multiple linear regression over and above those that we have examined in simple linear regression. So what am I trying to emphasize here? All those assumptions that you have tested in simple linear regression, you should also test for that when you're doing multiple linear regression. So that's why if you are solid in simple regression, you just have to bring in those techniques into multiple linear regression. Only that there's an additional assumption here, and that's the assumption of non-multicollinearity. So what is non-multicollinearity? In simpler terms, what we're seeing here is that the predictors should not be greatly multicollinear, meaning they should not be super highly correlated with one another to a point that you cannot anymore distinguish one from the other. So, say for example, if age and gender is one, if the relationship is one, then you will not be able to parse it out. Imagine the Venn diagram that I've shown you earlier. So if it's perfectly related, then maybe just using one predictor will suffice for you to make the conclusion that you want. So we don't want them. We want them to be uh we want them to have some unique contribution to the model. So in terms of collinearity, there are statistics used. These are also like if you're using SPSS, it's generated there. If you're using R or other softwares, you may have to call in specific functions to generate this. But the commonly used statistics is tolerance. It's the unique contribution of a predictor on the outcome, and that's a rule of thumb there. It should be 0.10 or great or greater. The variance inflation factor is another statistics, which is simply just the the value of the tolerance is a denominator under one. So one over tolerance or one divided by the tolerance, that's your variance inflation factor. If it's 4 or greater, then you need to examine your model. If the variance inflation factor is 10 or more, then there might be a serious issue. You will also be able to have a to eyeball this, like if you do a correlation before you do the regressions, they vary correlation even before you do the regression estimates. So this is just something that you have to be mindful of. Okay. So that's multiple linear regression. Now let's proceed to the the uh crux of the matter here. Right? So we have this slide, which I like. It's a quote which says, cause and effect, means and ends, seed and fruit cannot be severed, for the effect already blooms in the cause. The end pre-existing the means, the fruit in the seeds. So life as we know it is a series of intricately connected events and causes and effects, something we need to consider also when modeling reality. So we started with this model, distressing event leading to alcohol consumption. But there might be other variables at play in this model. There could be something in between them. And thus, we need a different approach for that to factor in that uniqueness. As you can see here, I have a belief that distressing event is directly associated with alcohol consumption, is associated with alcohol consumption, but probably it's because of the negative affect that the person is feeling after the distressing event. So it's not a direct association, but rather an indirect mechanism through the negative affect. And this is where mediation comes in, because mediation model is simply a simplified representation of a mechanism underlying the association between an explanatory variable, which is distressing event, and an outcome variable, which is alcohol consumption, via a mediator variable. So mediation usually is represented using this picture here. So independent and explanatory variable in blue is associated with the mediating variable in orange, and the mediating variable is associated with the dependent variable outcome, and there's still a line below, and each arrow is labeled as A, B, and C prime. In more modern discourses, usually mediation model is also referred to as an indirect process model, because the process involved in the relationship between the independent or explanatory variable and the outcome uh, takes place indirectly through an intervening variable. So this is another way of representing our uh, mediation model, our belief about the association between distressing event and alcohol consumption. So we label the explanatory variable as X, our alcohol consumption outcome as Y, and then we are using M to denote the negative affect. Okay. And the letters that you are seeing here simply are the the slopes of the association between the different variables in the model. So A here is usually the association between the X and the mediator. It is also called path A or A path. The B path here is the association between negative affect and alcohol consumption. And the C prime here is the direct effect of distressing event on alcohol consumption. So representing it algebraically, this is what we see. So here, you are actually working on two or even three if you want to include the C equations. The equation on the top is really what you want to estimate. So because this is you are curious about the Y. So in a mediation model, you see the Y here, the dependent variable, the outcome is equal to the intercept, which is again still the value of the outcome when all of the predictors are zero, plus the slope of path A, M, plus the mediator, plus the slope of path C and the independent variable. And your mediator here is in a way another outcome. So this is as you can see here, negative affect in itself is also an outcome. It's also an outcome of distressing event. So you have to consider this as well, and this is represented by another formula. So the mediator as the outcome is represented by the intercept. That's the value of the mediator when distressing event is 0 plus the slope of the slope, then the independent variable. And C prime here is the direct effect of X on Y. So these are just uh, some formulas that you are seeing, because this is what we've been doing since we were doing the simple linear regression. So again, you can represent it using the Venn diagram. This is familiar to us because simply, as you can see, as you will have probably realized now when looking at this Venn diagram, the mediation essentially is also a multiple regression-ish problem because you have two predictors of alcohol consumption, distressing event and negative affect. And this is basically what the formula is doing as well. The only unique thing about the mediation is that you have a theory in mind which positions negative affect in a unique place, uh, which makes it also an outcome of the the focal explanatory variable, which is the stressing event. So how do you make sense of a mediation? There are there's a long history to this, but the well-cited procedure where these all started is the Barron and Kenny paper in 1986, wherein you evaluate the association of X and Y first. That should be significant. So the association between distressing event and alcohol consumption should be significant. That's your first step. Then you evaluate the A and the B independently, and then you evaluate C prime, which is uh the effect of uh X on Y. It should not be significant anymore because the assumption in this way of looking at the model is that the negative affect should fully account for the association between X and Y. So if really there is a mediation from this way of looking at things, then the C prime should not be significant anymore. This line between X and Y should not be there anymore. Should be fully indirect. But there have been issues raised on that approach. It's too rigid. Like X and Y should be significant first in modern discourses. That's not usually applicable anymore. The C prime or the relationship between X and Y should no longer be significant but in reality you can have multiple mediators, and uh there really are situations wherein there are actually seldom that the direct association between these two are not significant in most data sets that we worked on. Okay. So A and B, the path A and path B is expected to be significant. However, in the next session that we will have next week, you will see that there is a possibility that the B or one of the path is not significant, not because they are not related, but because there is another variable acting on them. And that comes in the role of a moderated mediation model, which we'll talk about next week. And there's also a lack of direct testing for indirect effects using this model. Now, another way of looking at it, which is uh, uh, proposed by Judd and Kenny, it's a little bit earlier, is the use of Sobel tests. So you estimate the model. So you have the parameter estimates, then you examine the distribution of A and B. So essentially, the indirect effect is nothing more than just the product of the slope of A and B. And the total effect is the sum of that indirect effect plus the direct effect of x and y. So in M plus, it's very easily implemented. You can use model indirect function. So you just have to type this another line of code, a model indirect. And in this model, indirect effect should be significant. The more important thing is the association between path A and path B. Now, the only problem with the Sabel test is that its assumption is that the value of the indirect effect is normally distributed, which is not always the case because it's a product of two terms and it's not always normally distributed. So if the assumption is not met, then you put to question already the use of the test. There are still people who use Sabel test right now, and there's also a nice website if you want to use that to test your mediation. Now, in the more, I would say, more modern approach is to focus only on the AB or on the indirect effect. And that is through the use of bootstrap method, which is simply you draw an n number of bootstrap samples from the data that you have. So bootstrap sample is it's random with replacements. You randomly pick the data, you bring it back, you randomly take a data. So it's done automatically by the software. Then the software also calculates AB, the indirect effect and confidence intervals for that. And it gives you a 95% confidence interval which you use to determine if the indirect effect is significant or not. So it's not anymore the p-value that you look at, but the confidence interval. So these are just the functions used in M plus to implement that. You can also do this in R. Uh, in Jamovi, there's also a small function there where you can do bootstraps. So the model estimation looks like this. So there's a fabric, again, using the same data that we have. So as you can see here, this is our model on the left, schematically presented, and the simple mediation syntax is on the right. If you see there, we still see the simple regression model that we estimated, right? Alq's on distress. So distress being the X and Alq's is the Y. But we added negative affect as another predictor. So the first line here in the model reminds us of a multiple regression. What is unique here is that we're also representing in this syntax our belief that not only negative affect is associated with alcohol use, but that negative affect is associated with distress as well. That it is actually through negative affect that distress is associated with alcohol use. So mediation model is a representation of a belief about the association between and among these variables. So model indirect, as you can see here, is the function that I mentioned earlier, that it does as is it made use of Sobel if you do not call in interval, C interval function here, if you do not call that in, M plus will provide you with the Sobel test. So you have to call in C intervals, VC bootstrap if you want to use the bootstrap method. So at the decision again lies on you as the analyst, considering all the limitations and the affordances of specific techniques, as what I have mentioned earlier. So Sabel test makes the assumption that the indirect effect is assuming a normal distribution. The bootstrapping doesn't have that assumption. So again, we see the unstandardized estimates. Uh, as we can see here, as you can see here, the value of the stress is 0.259 negative as and its value associated with alcohol consumption, negative affect negative affects association with alcohol consumption is 1.224. We will interpret it the same as uh the we interpreted the regression model, and the same with the standardized estimate.
Doctor? Hi, sorry to interrupt, but it's about time. But before we go, I mean, we're gonna continue this. Okay, so guys, we this is a two-part series, and we'll continue this again next week. But before we go, there are several questions. There's two questions that maybe you can address, sir. The first one is something to do. Does residual simply mean outliers? I think you mentioned this briefly earlier, but maybe you want to elaborate more. Or
Yes, thank you
residuals and
very much.
outliers the same?
No, they are not the same. So I'll go back to that slide. And thank you, Miss Verna, for this is really a good time to cut the sharing. So at least we all have an overlook or a view of what mediation looks like. And as I mentioned earlier, it's basically just expanding our model and making use of more fancier statistics to do that. So let's just clarify on the residual and the outlier. So the residual uh is simply this one. So this is the purple line is the estimated line. So you have run your statistics, you have run your regression, and you have like a pattern, with a line here which shows a pattern of the relationship between your x and your y, and each data point would have some deviation from that pattern. So the residual is actually that deviation of each case from the computed slope or the line that you have. So this is an error. The outlier, on the other hand, is so the residual is in the context of your estimated model. The outlier, on the other hand, is something to do with the the data itself. So say for example, you have distressing event, the number of distressing event. So you have 5 participants in the study. So this one says 2, 3, 2, 3, and you have 100. The fifth participant answered 100. So that's a totally weird score there, because most of them are only saying 2 and 3, majority, but there's one saying 100. So that's an outlier. It's a unique, it's a weird case in the data that you have.
Thank you, sir. So those are extreme values for the outliers. And then this is the last question. Is there a suitable sample size for what's the recommended sample size for doing a simple linear regression and a multiple regression?
Yeah, so that's an interesting question, and there's a that's a whole discussion in itself. It's estimating sample size. There is a nice software that we use, G Power software, wherein you use that software to key in the number of predictors you have, and that gives you the sample size that you need for you to be able to estimate that kind of model. So if you only have one predictor, roughly 90 or 100 will do. But like if you use that G power, if you have one predictor, but as your predictor increases, then the number of samples also increases. So there's really no specific number in terms of the sample size, but it also depends on the complexity of your model. But if you have just one predictor, 90, 100, I will usually give you you can actually make use of this.
I have
Another consideration is also the number of parameters that you are estimating.
sorry, sorry to interrupt. I actually I have put in the chat box link for downloading the G-Power. This is free and this is provided by the University of Dusseldorf. I hope I pronounced that correctly. We'll continue the discussion. We are like almost 5 minutes over time. We appreciate all of you guys staying with us past the past the allotted hour. We appreciate your presence very much. And we also want to thank Dr. Bator for his very thorough um, presentation. We appreciate that as well. And we all hope to see you next week. That's gonna be on the 16th. Am I okay? I'm lost sometimes in time. So, but we'll see you again. And if you have registered, there's no need to re-register. We will send again the link for a reminder when we're about to begin the webinar. And feel free to share this with some of your colleagues. Again, thank you so much. We appreciate all of your presence and we hope to see you again next time. Thank you and have a great day.